So, good afternoon, everybody. Welcome to the third PCCL webinar. My name is Gernot Oreski. I'm Division Manager here at Polymer Competence Center in Leoben for the Smart Material Testing Division. And today I have the honor to introduce you to my colleague, Petra Christopher. She's a PhD student and co-worker in my group. And since 2.5 years, she's working on, let's say, exploiting the nanoindentation for polymers. And today she will tell you about her progress with different materials and different specimens, and also show you some very nice correlations to macroscopic mechanical testing. Before we start with Petra, just an announcement. The next webinar will be on July 13th. It will be held by Matthias Morak, and he will talk about material modeling of polymers and especially show you, let's say, nonlinear modeling and also short-term crash behavior, modeling of short-term crash behavior of polymers. With that said, Petra, please continue. We're looking forward to hearing about your results in nanoindentation.
So hello and good afternoon, everybody, and welcome to the webinar today with the topic mechanical characterization of polymers by nanoindentation. My name is Petra Christopher, and I'm working together with colleagues from Montan, Universität Leoben, and TU Graz. So let's start with common indentation tests. Common indentation tests are tests for macro hardness, micro hardness, and also nanoindentation. The common tests of macro hardness are Vickers, Rockwell, Brinell, or Noob test. And they work in the force range of 1,500 Newton to 10 Newton, and they have a rather high indentation depth of 1 millimeter. In contrast to that, the micro hardness works with Vickers or Noob indentation and has a 10 to 1 Newton indentation force. The indentation depths here are big, more than 0.2 micrometer. Nanoindentation is an instrumented indentation. And here we have the advantages that there is no optical observation required. We have automatic measurement of hardness, and there is no user dependence. We are working in force regimes of 1 Newton down to 0.01 micronewton. And we have very shallow indentation depths of which are smaller than 0.2 micrometers. Here on the right side, you can see a typical force penetration curve of nanoindentation. We have a loading phase where the force is going up, and then an unloading phase where the force is going down. And from this unloading phase, we can get also the elastic modulus by the method of Oliver and Farr. Why do we use nanoindentation? We can use nanoindentation because we want to measure on a reduced scale, which you can see here on the right side. There is a small area of interest, and in this small area we can do nanoindentation. We can also measure only surface properties, or we can do nanoindentation if we have only a small amount of material available. Furthermore, we can measure components in a multi-phase, on a thin film, or in a multi-layer. You can see down here in this picture that when we do a large indentation depth, we can get the response of the homogenized material. But if we do shallow indentation, which you can see here in yellow, then we can get the properties of the different phases of a material. So what's now so specific about nanoindentation of polymers? When we do nanoindentation of polymers, we have viscoelastic creep on this unloading curve. And the power law fit of Oliver and Farr, which I explained before, is only limited applicable to this response curve. You can see it very good in the on the left on the slide that we do nanoindentation in the same material, but with two different holding phases. So one, we have a 10-second holding phase, and in red, we have a 100-second holding phase. And we get two different unloading curves. And from these two different unloading curves, we would get two different elastic moduli. But this can't be true. And on the right side, you can see a typical nanoindentation curve in a viscoelastic polymer. Without a holding phase, you see this typical nose building, which leads to a wrong elastic modulus. So what are now the objectives of nanoindentation at PCCL? First of all, I will give you just a classification of polymers according to the molecular structure. We have 4 different classes, which are amorphous thermoplastics, which are uncured, and typical examples are PMMA, PC, and PS. For the semi-crystalline thermoplastics, which are also uncured, we have typical representatives like PE, PP, or PET. Then we have the group of elastomers, which are white meshed, and with the representatives a natural rubber or butadiene rubber, and the thermosets, which are epoxy resins or melamine resins. The goal for PCCL is now to deliver a method for every polymer class to be investigated by nanoindentation. Typical application examples for nanoindentation of polymers are, which you can see on the left side, microelectronics. Here we have an embedded sample, and if you want to investigate a special region, you could use nanoindentation to get the elastic modulus or the hardness of this special region. You could also investigate, for example, varnishes, because you have here only a thin layer, and this could be investigated with nanoindentation. Furthermore, you can investigate multi-layers, for example, here photovoltaic modules, or if you have injection molded components and you want to investigate a special region of them, you could also use nanoindentation. A last example would be foils or thin films, which could be investigated from the top, but also if you want to in a cross section. Now I will show you 4 examples of my scientific research here in PCCL. First of all, I want to show you how to get the elastic modulus of an amorphous thermoplastic. Furthermore, I want to show you how to get the elastic modulus then from a semi-crystalline thermoplastic. I also want to show you some hardness measurement tests and creep measurements on a very thin films. So I would like to start now with the amorphous thermoplastics, where we have chosen PMMA as a material model. You can see here the PMMA sample on the right side. PMMA is a thermoplastic, and it has an expected elastic modulus between 2 and 3 gigapascal. The sample here is amorphous and very homogeneous. It has a flat surface, and this is very important for nanoindentation to have a flat surface. And of course, PMMA is viscoelastic. The goal of these investigations here are to get the elastic modulus of PMMA by nanoindentation and to validate this nanoindentation data by compression tests. So let's start with the standard nanoindentation, which is the before described Oliver and Farr method. Here on the left, you can see the indentation curves on PMMA. We did here indentation with a large spheroconical indenter tip. You can also see here the tip form on the right side of the screen. The modulus we got out here with the Oliver and Farr method is 3.3 gigapascal. So this is in the range of the specification of PMMA. Furthermore, the indents on PMMA are very homogeneous, and we cannot see any nose building like described before. But of course, the viscoelastic creep occurs also on the unloading phase. So what we also did on PMMA were creep measurements. Creep measurements are to load rapidly to avoid creep in the loading phase, and then hold a longer time and let the material creep in this longer holding phase. And this you can see here on the left side, that a material here is creeping, so the indentation depth is going up. And with this creep or this time dependency, we can use it for viscoelastic material modeling, which you can see here on the right side. The simplest model for creep modeling are the standard linear solid model, or a bit more complex, the general Maxwell model of order 2. These material models, they consist of springs and dashpots, whereas the spring is the elastic or the restorative component, and the dashpot is the viscose or the damping component. These models assume that we always stay in the elastic regime. And for nanoindentation creep modeling, the SLS model is the one that is mostly used. Another thing is the choice of the contact model. So how is the indenter contacting the sample? The Hertz contact model, which is a spherical contact model with a plane, is the one mostly used for nanoindentation. Another model is the JKR adhesive contact model, which is used when we have smooth surfaces, or one of the contact partners is made of a soft material like a polymer, and if van der Waals forces play a role like in a microscopic system. And here on the left, you can see that this contact area for Hertz is smaller than for the JKR model. So for modeling the PMMA, you can see down here, we used the SLS model together with the JKR contact. And with this modeling, we got an R value, which is the fit quality of 0.99, which is quite high. And an E0, so an elastic modulus of 3.5 gigapascal. So now, if we compare now those nanoindentation data with IFM nanoindentation and with macroscopic test, we get here these results. But first of all, I would like to show you the compression test on the right side, where we used 5 samples of PMMA, and we got from this compression test, which is a common macroscopic test, a stress strain curve, and calculated here the modulus from the slope at the beginning of the curve. And if we then compare those results, so in blue the compression test, the macroscopic test, to in black nanoindentation, the simple Oliver and Farr method, or in red the nanoindentation with the modeling. And in pink, we have also AFM nanoindentation with the GM2 modeling. And what we can see here is that those measurements, they are in good agreement with each other. And there is also about this topic a publication from me and my colleagues from Montana Universität Leoben, which you can see here at the bottom of the slide. Next, I want to show you the investigation of a semicrystalline thermoplastic, and this we choose here the POM as a model. POM is thermoplastic, and has an expected elastic modulus between 2 and 3 gigapascal. It's semi-crystalline and has a rather high crystallinity of 70%. The sample also has a flat surface and is viscoelastic. And what you also can see here at the right side of your screen, that we have a high crystallinity, and the crystallinity is not homogeneous all over the sample. So we have at the edge of the sample a lower crystallinity and a higher crystallinity in the middle of the sample. And the goal of these investigations with nanoindentation was to get the elastic modulus of POM by nanoindentation, and again to validate the nanoindentation data by compression test. The challenges here were that we have microscopic effects like surface roughness of the sample and the semi-crystallinity, which influence the results. So next, I would also like to show you now first of all, the data modeling or the creep modeling of the POM investigations. I have here the indentation depth over time curves, so the creep curves. And in red, I have a measurement and a simulation. The simulation are the dots from the center of the sample. And in black, we have measurements from the edge of the sample. What you can see here is that for the edge of the sample, we have a higher indentation depth here than at the center of the sample. And also when we normalize the experiments, you can see that we have higher creep at the edge of the sample in contrast to the center of the sample. So we took now these creep measurements to calculate the complex modulus, which consists of the storage modulus and the loss modulus. And with the formulas down here, we enabled a spectral representation of the viscoelastic modulus. And in the graph here, we can see that, again, the loss modulus is the storage modulus, which is the elastic contribution. And the loss modulus is the viscose contribution. And in the graphic, you can see that the loss modulus is the same for the edge and the center, which you can see down here in the graph. And the storage modulus differs for edge and center. So the differences of the elastic modulus for center and edge originate from the elastic contribution of the viscoelastic POM. Now I did nanoindentation measurements over the sample of POM, so over the cross section, which you can see down here. So I have indents here in this region where we have less semicrystallinity, and when I'm going deeper into the material, we have higher semicrystallinity. And when I do now nanoindentation, you can see here in blue the Oliver and Farr indentation, and in orange creep modeling indentation, the creep indentation. You can see that for both measurements, we have lower elastic modulus at the edge of the sample and a higher elastic modulus in the center of the sample. Furthermore, the Oliver and Farr indentation results, they fit to the results of the compression test. And the mean modulus of the Oliver and Farr indentation is in the range of the compression test. But the creep modeling also has a lower modulus at the edge of the sample and a higher modulus at the center of the sample. But these measurements are overestimating the Oliver and Farr, the compression test, and also the specification. So we think that this GM2 model is too simple for the complex POM structure. And for the modeling, we also used parameters like, for instance, the Poisson ratios that are taken from literature. And therefore, the modeling overestimated the all-over and far indentation. So if we take now a closer look at microscopic pictures of the POM, we can see here on the upper side a part of the edge of the sample. We have here once the sample unedged, and down you can see the sample edged. And here we can clearly see that we have a layered structure at the edge of the sample, like the skin layer, which is a more amorphous zone. Then we have the shear layer, which is a transition zone, and the core layer, which is a more crystalline zone. And from these microscopic pictures, we estimated a spherulite diameter of about 20 micrometers. And these spherulites consists of lamella and amorphous zones in between, and the lamella thickness is only 10 nanometers. So now we investigated this semi-crystalline POM also with another very common indented tip, which is the Berkowitz indented tip. You can see it here in pink. The Berkowitz indented tip is a three-sided and very sharp indented tip. And in blue, we have again here the spheroconical indented tip. What we can see when we investigate POM over the cross-section is that the all-over and far measurements with the Berkowitz indented tip overestimate the values from spheroconical indenter with all-over and far method. And this is because when we indent with Berkowitz, the Berkowitz has a sharper tip, and here we have more increase of contact error with depth. This causes a higher strain, and therefore we have more plastic and less elastic response. And as I told you before, the all-over and far method deals only with elastic recovery, and therefore Berkowitz overestimates here the spheroconical indented tests. On the right side, here we compared the diameter of the indenter imprints. So how big are these imprints from Berkowitz and from spheroconical indenter over the cross section? And we can see here that the size of the imprints are homogeneous all over the sample, but we have bigger imprints, of course, for the spheroconical indenter tip. And the imprints of the spheroconical indenter tip are in the size range of the spherulites. So the spherulite distribution influences the nanoindentation results. As a next topic, I want to show you thin film investigation at elevated temperatures. We had here a sample, a metal sample, which was covered with 1 micrometer silicone, and we wanted to get creep curves at different temperatures from this very thin film. And you can see here on the right side, we got creep curves here for 22 degrees and also for 80 degrees. We got these creep curves for really shallow indentation depths, which are only 0.3 micrometer. And we got also for the 80 degrees more creep for higher temperatures. So the outcome of these experiments was that it is possible to measure creep of a very thin film. Next, I want to show you some hardness measurements on an elastomer. We wanted to do hardness measurements on a rubber, in shore A and at very precise positions. The challenge here was that the sample was too small for conventional shore A measurement device. As you can see here on the left side, the shore A measurement device needs some space. And the solution with nanoindentation was we did hardness measurements on 3 different samples of the same material. First of all, with nanoindentation in Vickers, and second, with conventional shore A measurement device in shore A. And then we did for these samples a regression time. And then we did nanoindentation on the small elastomer sample to get the hardness in Vickers, and we calculated the hardness in shore A with the before done regression line. What you can see here for this example here is that position 1 exhibits smaller hardness than position 2 and 3, and we can say that local measurement of the shore A hardness on a small sample is possible. We also did hardness measurements of 5 polypropylene samples with slightly different composition. And you can see here on the left side in blue, we did nanoindentation to get the elastic modulus, and also shore D hardness measurements in orange. And for these 5 samples, the elastic modulus and the shore D hardness are correlated to each other. So we have a good correlation between nanoindentation and shore D hardness. And on the right side, you can see microtribometer indentation. And what we can see here, these are the same samples then on the left side. When we have a good correlation between nanoindenter and microtribometers, because the samples with the lowest hardness, they show the highest indentation depth, which is here this ST2 sample, which has the lowest hardness, and on the right side, the highest indentation depth. So also this correlates very good. Now I would like to give you a short summary. So we have seen if we want to indent an amorphous thermoplastic and if we want to get the elastic modulus, we should use a spheroconical indenter tip with a large radius. And the method for evaluation here, we can use the simple Oliver and Farm method, but we could also use the creep in combination with material modeling. If we investigate a semi-crystalline thermoplastic and we want to get the elastic modulus, we should also use a large spheroconical indenter tip. And as a method, also the Oliver and Farm method is good enough. But we could also use a creep measurement in combination with a more sophisticated material modeling. If we want to measure the hardness on an elastomer, I would recommend to use a Berkovich indenter because it has a more defined and precise geometry. And when we measure with hardness, we are dealing with imprints, and therefore the Berkovich, I think, is a better choice. And here we also use the Oliver and Farm method for hardness measurement. The conclusion of my presentation is that it is possible to measure the elastic modulus of amorphous and semi-crystalline thermoplastics, which are comparable to macroscopic tests and which are reproducible. Furthermore, it is possible to measure the elastic modulus or the hardness on small sample pieces or in special regions of interest. And it's also possible to measure creep of very thin films. In the end of my presentation, I want to give you a short outlook what I will do in my future research. I would like to investigate polypropylene, which you can see here in the pictures. Polypropylene is also a thermoplastic semi-crystalline polymer, but it has a lower crystallinity than POM, and it has also bigger spherulites. What I also want to do is to investigate the influence of polymer aging on nanoindentation creep behavior. You can see here on the right side a picture from literature where we have aged and unaged samples. The aged samples are the dashed line and the unaged samples are the solid line. And you can see here that the creep curves are decreasing after aging. And what I want to do is I want to investigate polyethylene in cross-section in different aging degrees and compare these to each other. So this was it from my side. If you have any questions, I would be happy to answer them now.
Okay, thank you very much, Petra. So while we will go over the first few questions, you still have the possibility to post other questions in the Q&A chat, so please go on. So the first question is it possible to measure in media, and what effort does it take? Or
okay, yes, it's possible, for example, to measure in fluids. So we also have a kit to measure in fluids, like water. It's, I mean, the sample has then to fulfill more requirements. See, the size of the sample shouldn't be too big, but yes, it's possible if you want to measure in a fluid.
okay. Second question, is there a specific requirement from the material or the sample surface to make measurements using nanoindentation? Examples like roughness, modulus, or hardness limits, etc.
Yes, I mean, for nanoindentation, the surface roughness should be really low. That's the requirement. So the higher, there are some roughnesses where it's not possible, then where you cannot measure then anymore. But if you have a low roughness, I can measure, and but there is then a higher standard deviation. If the roughness is going down, the standard deviation is going down.
And the second part is, are there limits in modulus or hardness?
No, I mean, for my device, there are no limits in module. I mean, okay, for my device, the modulus or hardness shouldn't be too low. If we're going to gels or something like that, or to human tissue, this I cannot measure anymore.
But that means also with the nanoindenter that we have, we can measure, for example, ceramic surfaces or metal surfaces without any problem.
It's also possible, yes, it's no problem.
So it's the surface roughness, the toughest one. Okay.
Yes.
Next question. Could you please explain about the sample preparation in all cases? It just popped up, so.
Okay. Sample preparation, for example, you mean for the PMMA sample, this was just the flat sample. This I got it from a customer. But for the POM sample, we embedded it in epoxy resin, and then we grind it and polished it with a grinding device here at PCCL. Down to, I guess, what was it? 1 micrometer polishing paste.
So I guess it strongly
So
depends.
this is the sample preparation, what we do.
I guess it depends on the material class as well. I guess for elastomers, you don't need that much sample preparation as for harder materials, I guess.
Yes, for the elastomer we had here in the presentation, I just glued it to the sample holder and measured it. So this was a straightforward measurement.
Okay. Another question, what was the criterion for the surface roughness? So is there a value that you can tell, so like an RMS roughness or so?
Mm-hmm. Yeah, I mean, from my experience, it was that the PMMA sample had a roughness of 10 nanometers, so it was really low. And you saw it in the indents that the indents were quite homogeneous. And for the POM sample, we had a higher roughness. It was, I think, 30 or 40 nanometers. And the indents then were more inhomogeneous. So this is the range where I'm working in the nanometer range of roughness.
Okay, one final question regarding to the elastomer samples. They were vulcanized, or so they were cross-linked?
Yes, I guess, but I don't know exactly because this was samples from a customer.
Okay.
Don't know much about them.
Okay, next question. They're popping up very fast. Right, so good to know. You state it is possible to estimate the elastic modulus via nanoindentation. What about the viscoelastic properties? You showed something about loss modulus. How accurate is that? Could you please give some more details on how you obtain it from the creep data? Thanks.
Yes, I could go back to this here because if you're interested, there is also a publication about that. You can see this here on the bottom of the slide.
I can post the link. Okay, it seems we lost Petra.
Creep data. No, I'm here.
Okay, then I was lost. Yeah, you froze for a second. I can post the link to the paper for anybody who is interested. Maybe Petra, this question is also related. So we can measure dynamic mechanical properties as well with the nano.
Yes, we can also use. There is the so-called sinus mode, where we overlap the nano indentation with a sinus mode, and from this we can get the elastic, the storage and the loss modulus of the sample. This is always in nano indentation. It's called I think CSM, but this method was not the focus of my work until now.
So possibly next year, maybe
Yes.
we have some more results on that, but we were going step by step. So last question, what would be the main challenge in measuring aged polymers?
Yeah, I think the main challenge is that it's for aged polymers, it's not that the elastic modulus will change. It's more that the creep will change for the aging, for aged polymers. So this will be and I want to correlate if the aging properties, how is creep changing when I change the aging properties, like the temperature or the time, or yes.
Okay, that's also a thing we are doing currently, and hopefully next year we will have some results on that as well. Okay, no other question. With that, thank you very much for joining our webinar. Next webinar is in July about material modeling, mechanical modeling of polymers. Just as today, register, it's for free. And we're looking forward to hearing and seeing you then. And with that, thanks Thank you very much, Petra, and also thank you, all of you, for joining, and see you hopefully soon. Goodbye.